Okay, hello everyone. Welcome. So we're gonna talk about, okay, so it's been a bit of a slow month. I think everybody has been at conferences and I had vacation. But we'll still go over the normal like PRs and issues and stuff. And then at the end, I will give a presentation about the layout system, which I have some slides for that. So we had 36 PRs since the last time. There was a bunch of work on the front end. So we have new support for conditionals and if statements. There were a bunch of bug fixes for the type system, and then support for Mac OS. So I did some work to basically prepare the front end so it can be packaged on as like a pip wheel, and all of the like build dependencies can be included with that. And so the next step is to actually like ship it on PyPI. So I was working on that. There's been a bunch of work done on the RLWE pipeline for the layout system and polynomial approximations. Yeah, I think the big things on the polynomial approximation side, we have a new internal contributor at Google who's very excited about it. And so he has been working on a Chebyshev version of, so I made this kind of mistake early on where I was doing the polynomial approximation for like ReLU and stuff, and I converted back to the monomial basis, and it turns out that is like already numerically unstable, and then I tried lowering using like Patterson-Stockmeier in the monomial basis. So then I realized that was a mistake, and now he is doing the work of doing the lowering, keeping everything in the Chebyshev basis and doing the lowering using like the Chebyshev Patterson-Stockmeier method. So I think there's actually a draft PR that has that out, and he hasn't asked me to review it yet. But so as a consequence of that, the lowering for polynomial eval has moved into its own pass and gained a few options. So there's some PRs around that. Yeah, and then there are some improvements to the existing lowering using like iterated squaring and stuff. So he was just getting started and doing some like test changes to make sure the build system worked. Okay, what else is there? Yes. Okay, so I'm still in the process of integrating the like end-to-end layout system that I'm going to give us slides on next. And the last remaining issue is that I'll talk about this more in the talk, but the plain text backend that we defined doesn't have any of the packing information. Like, it doesn't have its own client helpers in the plain text backend. Like when you want to run the program without, so the context is you can lower a high-level program to like secret arithmetic, and then you can lower it to one of our different schemes and then continue. The plain text backend is one of those schemes where you basically say, okay, forget that we're doing cryptography and just run everything with all of the packing still in place, right? And all of the lineage kernels, run it just with plain text arithmetic, and then you're not doing any encryption. That's like a helpful thing. But the problem is that when we have the client helpers that do the encryption and decryption before you actually run the main program, those are only at the LWE dialect, not happening before it gets lowered to scheme. And now the packing information is part of those. And so we want the packing information to be included as part of the plaintext backend. So I have to basically move that add client interface pass higher up. And there's a bunch of complications for how to organize that. Okay, and then there was a bug reported about situations where the multiplicative depth of the pipeline was like 0, and it was causing OpenFHE to complain. So that was fixed. So on the noise side, I think there are just a few bugs on the noise analysis. Oh yes, okay. There was some build issues with the Python front end that caused me to do some like minor refactoring. And then I think Hongren was working on some more of his work where larger and larger circuits got noise that was too big to represent, and so he changed it to represent things in log scale. Okay, for the build. Okay, what did we do on the build?
Jeremy, do you want me to go over the rest of it, and you can save your breath for the layout system? Okay, yeah, because
I've been sick, everybody. Sorry.
Yeah, I have some context because I had to go through this. So for the build, nothing was too crazy except some of these were for integrating the CGGI pipeline into the front end. So there were some minor fixes there. And then Hongren also reported a bug, and Jeremy added the math backend to be the default when you Bazel build OpenFHE. And then there was also an Apple crash on an older version, so the Bazel lock file had to be updated. And hopefully we'll improve that by doing like some automatic, like once a week lock file updates, TBD. And then on the CGI pipeline, most of this work was me. So, and then Voucher also improved some of the things. So very quickly here, a lot of this was fallout for the AES demo, which is a in progress PR. There was memref global replace, which is the one that extracts out the constants from global memrefs to like inline them. Those would only work with affine loads, so it's fixed now for memref loads as well. And there's other couple bug fixes. And then miscellaneous stuff. Hongren did give a presentation recently about the management dialect, so the docs and slides are in that PR if you want to check them out on the blog now. And then there's some other bug fixes. And then Muthu also contributed some graph utilities for their project. So we'll see where that gets ended up being used if we can. But nothing else too crazy there. So on the in progress PRs, Hongren, okay, you are here. So Hongren, I didn't go through the 1817 at all. Is there any quick words on that?
So recent attacks highlight the dependency. So in noise analysis, we need to track the dependency, and a symbolic way is a good way to handle that. And the other refactoring stuffs. That's all.
Okay, awesome. Yeah, I'll take a look. I know the descriptions are always pretty in detail. On the front end support, Alex added some tensor support, which includes like a shape inference pass as well to resolve the shapes of the tensors. And then there is also, this might be a draft PR. Yeah, it is. Okay, this is in progress PRs. The CGGI scheme is also added into the front end. It will fail because we can't compile any of our CGGI backend code with Clang the way that we do with OpenFHE, because we don't have like OpenFHE's bin FHE version to implement CGGI. So it will just fail. Honestly, I think actually I'll just ping that for review. It can just merge as is. It will still generate the CGGI dialect code and the intermediate IRs. For analysis. And then Jeremy also did some shifting around of the propagate annotation code to reverse propagate. The Chebyshev, as Jeremy mentioned earlier. There's also the AES demo is in that draft PR pending internal merging, which requires some like updates of the TFHE Rust crate internally. But if you check that out, you can run the AES demo with like a Bazel run command on CPU. And then, right, kind of cheekishly, I also put in Jeremy's big migrate arithmetic FHE pipeline to the new layout system, which we'll hear about later. That is currently still in progress.
And then there's 2 months. I'm sorry.
No, it's funny because it's like you can see the diff of like 1633 with like the current PRs in the 1800s. So it's always funny to see that. Notable new issues, it's been pretty slow, I think. So we did have, Alex had an office hours last week, and Claire showed up, and she was talking a little bit about, getting an experience using the front end with CKKS, and had requested a little bit of like how the user can customize that. And so this is like sort of a big tracking issue of how to support custom input scales for CKKS from a like user perspective in the front end. So some fallout work in there. And then there was also a paper on parameter selection as well, posted in that as like a research synthesis. And yeah, I think that was really all the notable new issues.
Okay, so I can go ahead and do the slides I have, and then we can open the floor for discussion. Okay, let's see. Right. That's not good. Hold on. Let me do this. Okay, does that look good to everyone? Okay, yeah, let me go back to the front. Okay, so yeah, these aren't going to be like super fancy slides, but I'm going to talk about the layout system. So, okay, here's like a like quick overview of like where the development status is. So most of the work that I'm going to talk about has already been merged, but is not like integrated into the main arithmetic pipeline that we have. So the remaining integration is in that PR. And in that PR, so all of the tests that are based on like, they're actually doing FHE are passing, but the plain text backend tests are failing. So that's like the main remaining issue. And I mentioned this earlier, but the packing logic that we have is we want that to be in the client helpers. So that's a good thing, but the plain text backend does not actually have any client helpers. So the packing is wrong and it causes the examples to segfault. So as I mentioned, the client helpers are specific to the LWE dialect right now. They add like LWE encode, LWE encrypt. And so I need to move that pass and figure out what that pass means when there's no longer LWE operations in it. And then I need to change the later lowerings from secret to scheme to interpret those ops and replace them with RLWE encode and decode ops. And I think that there's also like a bit more comprehensive testing that I could do on the different lineage kernel lowerings. So I have like, they're testing in isolation, but I don't have like big tests that like exercise like large scale programs that have multiple lineage kernels in them. So I think there's probably still some issues in there. Okay, so I'm going to talk about the sort of three aspects of this. The first is like, what is a layout and how do we represent it in HEIR? The second thing is the overview of the pipeline. And then the third thing is like all of the concerns I built up over the process of building this and things I want to improve. Okay, so layout representation. Originally, I wrote this design doc, and I'll share the slides, but I think most people have seen this. This was the doc where I went through and sort of justified why these decisions made sense. And so it starts with the idea that we're going to reuse the MLIR's affine map. But just abstractly, before we get to the implementation, a layout in this case is a mapping from the index set of a possibly multidimensional tensor to the index set of a set of ciphertexts, a tensor of ciphertexts. And so as the simplest example is, you know, the first two examples, there's only one ciphertext. But let's say you want to do like a row major, you have an n by 32 tensor and you want to flatten it into one big ciphertext. You can represent that by taking the 2 dimensions of the tensor and then doing sort of the obvious, like multiply the first index by 32, add the second index, and then it flattens it into one big ciphertext. Another example is a cyclic rotation that can be represented in some sense by adding like so modular arithmetic operations are allowed in these affine maps. So you can take the index, add it to +3 and do a modulus, and that will shift it to the right. And then you can represent the Halevi-Shoup diagonal packing. In this case, it's a 16 by 16 matrix packed into ciphertext of size 16. And this formula may look a bit unfamiliar. I will come back to that, but you can just trust me that that is doing the diagonal mapping. And so these maps are, they have quasi-affine operations. So in this case, that means that you can have all of the normal affine ops, multiplication by constants, addition, and then modular arithmetic by constants, and then also floor and ceiling with rounding, where the thing that you're division and floor and ceiling with rounding. So you can for division, also the divisors need to be constants as well. But so this is all handled by MLAR. Okay, and before I get to the next thing I want to say, I want to sort of define this distinction that we have. So we have the idea, because this packing stuff is all happening before we actually represent ciphertexts in the type system. And so we're doing everything here with just like tensors of clear text operations. We're packing things, and then we encode and encrypt. In this case, there's some like complications with the type system. So I define these. This is terms I made up. So one is the data semantic tensor. This is just user data in the common way that you would think about it. You have a 32 by 32 tensor of I32s. The user actually wants to think about their data that way. And then you have the ciphertext semantic tensor, which is what happens when you take the clear text data and you pack it into a plain text so that it can be encoded and encrypted. Basically, this is the slot representation of the plain text data. This is data in the form that the user can't really use it, but needed for FHE. And the complication that made me require to like define this concept is that the data semantic tensor and the ciphertext semantic tensor can actually be the exact same type. So if you're just looking at the type system alone, you can't tell if your data is packed or not. So for example, if your data just happens to align with the ciphertext size, right, the number of slots in the ciphertext, then the packing might be the identity function. It might be a rotation of the input. And so you can't even tell just by looking at the tensor that it's like what it is. So you have, so I use the word semantic to be able to say, okay, we have to interpret the type as being in a particular context. And I guess the alternative to doing this, which I don't think we had ever considered as a serious possibility, is to like make a completely parallel type system for packed tensors, packed clear text tensors before encoding and encrypting them. And the problem with doing that is you basically have to, you can't like operate on them without mirroring all of the upstream MLAR tensor types and ops. Okay, great. So when we think about these layout maps again, it turns out that by themselves, they're not sufficient to represent everything we want to represent in FHE or in packing. So the reason is basically that a layout map is a function, and functions can have to take the input and produce a unique output. You can't have one input go to two different, basically one input slot can't go to two different output slots without representing it in, as a multi-map or something. And so, but like packing in FHE famously has replication. And so we had to figure out some other way to represent that replication. So for example, this slide is basically showing off some of the choices that we might want to make. So say you want to pack a size 32 data tensor into a size 2048 slot plaintext. What do you do? Well, usually what we do is we repeat the input tensor sort of cyclically around, just like tile it basically. But you can also pad with zeros. Maybe you can pad with zeros on the left or the right. Maybe you can pad with ones if you're doing some operation where that makes sense. Like maybe you're trying to multiply all of the elements in the data tensor together. And so then if you're doing like a rotate and reduce thing, okay, I don't know, maybe you'd want to pad with something besides zeros. And then if you have like a multi-dimensional tensor and you're packing it into multiple plain text or multiple, ciphertexts, you might want to be tiling that horizontally, tiling it vertically. You might want to like replicate, like do Halevi-Shoup and then replicate that somehow. Like I think there are lots of exotic packing system options available. And so like just having the layout map, you just can't do any of this stuff. So for this, we came up with the TensorX alignment attribute. So this attribute basically describes all of the pre-processing that you're going to do to the tensor before it is before the layout map is applied. And notably, this allows you to basically make the input tensor bigger so that you can apply the map and get replication and do all of the different, all the things I mentioned in the previous slide. So an alignment in our case has input shape, which is like the original tensor, clear text tensor shape. It has an output shape, which is an intermediate shape before applying the before doing some stuff. I'll describe that. It has a list of new dimensions that you might want to insert into the tensor. It has padding per dimension, and in our case, the padding is only on the tail end of the axis. Then it has a padding value. So what this, okay, so I said this output shape. What happens is the output shape, okay, so when you do some stuff to the input shape, then there's like an implied replication and tiling along axes with compatible sizes to get to the output shape. This, I don't know how happy I am with like any of the decisions in this. I'll talk about that at the end, but I'm just describing what's in the code base right now. So in this example of this alignment attribute here, you start with a tensor of size 7. It will pad a single 0 at the end of that tensor to bring it to size 8. And then it says that the output tensor has size 16. And then the system recognizes that, oh, 8 is divisible by 16, so we'll do replication along that axis. Here's another example where another two-dimensional example. So here the input data is size 10. We insert a new unit axis in the first dimension. Then we do no padding on the first dimension, but padding of 6 on the second dimension. So that brings us to a tensor of size 1 by 16. And then the output tensor is size 32 by 32. So we take that 1 by 16 and we tile it in both dimensions because it's divisible in both of those dimensions. So this, I mean, this is like a lot. I think I have one more example, but if anyone wants to stop and ask questions, feel free. No, okay, that was actually my last example.
Maybe a very stupid a question about the last thing that you mentioned about the alignment. For now, like the multiplication, is that only supported for 1D inputs, or like can we go in the future from 2D to 3D inputs or something like that?
So what do you mean by the multiplication?
Yeah,
so
no,
like
now you say
okay.
like your input is, yeah, you're first going to make it a 1D vector out of it, like a 1 times 16.
Oh yeah, I mean, so the input, the layout system allows you to start with multi-dimensional tensors. Yeah. So you can, okay, I mean, it's arbitrary.
Like, that's pretty cool.
Yeah. So you could start with arbitrary input tensors, and then the output too. Like this layout system supports having like the ciphertext semantic tensor can be 3-dimensional, where the first 2 dimensions are just like normal tensor dimensions, and then the third dimension is the slot dimension, basically. And so the layout system doesn't stop you from doing anything like that. The support of our kernels for those are where we're lacking, right? Like the kernel might, like if you're doing like a matmul kernel and like a general matmul kernel and you've got like 8 axes, like, okay, I don't know what you're going to do in that case. I don't think we have kernels for that. Like even in the literature, right? But yeah, and I think like even like at a simpler level, I think if you have like a 4-dimensional tensor and you're doing a reduction along like the 3rd dimension, I don't think my kernel for lineage reduce can support that yet. So I think there is some work to do, but the layout system is, I think, flexible enough to support it if we have the right kernels. Okay, so after this alignment attribute, the layout itself is an attribute with 2 sub-attributes. The first is the alignment attribute, and when this is all lowered, that alignment stuff like materializes to HEIR that is applied first to basically do all of this expansion and replication. And then the affine map is applied to the aligned tensor to get the final ciphertext semantic data output tensor. Okay, so now I'm going to move on to the pipeline. And I'm actually, I think I've only got about 4 more slides. So the goal of this layout pipeline, there's sort of 3 goals. One is to select layouts for the data semantic tensor types. The second one is to pick a kernel for the lineage ops that need to be lowered. And then the last thing is to implement the kernels while also implementing the layouts. So this is broken down into 5 steps. So the first one is relatively simple, just simplify some lineage operations to prepare them for the kernels. And then the 3 big passes, one of them is layout propagation. That will select the initial layouts for the system. And this is following like Felipe in its organization. The second one is to optimize the layout choices. And so that will try to hoist any like layout conversions and layout incompatibilities up through the HEIR. I'll talk about that more later. And then convert to ciphertext semantics, which is the kernel implementation step. And then there's some cleanup that happens after that. Okay, so drop unit dims is the simplest one. Early on, we realized that like machine learning systems are like sloppy with their representation of the different ops. So like a matrix vector will be represented as a matrix-matrix multiplication with like extra dimension 1 units. So there's a pass that I added that will basically simplify all those unit dimensions and then like give ops their like proper names that we can target them more easily with kernels. Okay, then there's the layout propagation. So this one it sort of has like 2 purposes. One is to basically just like populate the HEIR with layouts. So it will start by looking at all of the like input operands and any clear text like instantiated like static values that just get like plain text encoded, and it will give them default layouts. It will propagate those layouts forward through different ops, and then it will identify which ops need some change to the layout in order for them to be compatible for that op, and then it will insert layout conversion operations when it encounters that. The simplest example of this is like if you're doing a lineage reduce. So there's a weird thing that happens here, that in order to do all this, you need to know the kernel of the operation that you're going through. Otherwise, you can't take 2 input layouts and know what the output layout is going to be. But for most of the kernels that we have, the input and output layout are like desired to be the same. So like Halevi-Shoup doesn't change the vector layout when it's done. And so in some of these cases, even we're kind of assuming we know the kernel, but it results in like a trivial just like pass through. But the simplest example where it doesn't is when you're doing like a lineage.reduce. So you have some matrix, you want to sum along the rows and sum along the columns. That will give you 2 different layouts from the result. And I don't think there's like a controversy about what kernel to use there. But the point is that you get the same tensor type of the results. So in the data semantic world, those 2 things can be added together and it semantically makes sense. But in the ciphertext semantic world, it doesn't make sense because one is row major and one is column major in their organization. Or no, sorry, they're strided differently is what it is. And so they have incompatible layouts, and you need to insert a layout conversion to realign them so that they can finally be added together. Okay, so the layout propagation, just goes forward and just like greedily inserts these layout conversions. The second pass, which is layout optimization, tries to resolve some of these layout conversions by hoisting them up into the front of the HEIR and then like folding them into other, the actual like layout assignment. So here, what you could do is basically, so it goes in reverse order through the HEIR, and it says for each op, if the output has had its layout converted, then try to hoist it up through the op and apply different potentially different layout conversion to the operands of the op. And if you could do that successfully and iteratively, and you get all the way to the top, then you might have situations where there's 2 consecutive convert layouts. Those can be folded together. And then there are cases where you have a assign layout, which is like a plain text, an op that assigns a layout to a plain text that's like statically in the IR, followed immediately by a convert layout, and you can just fold that into a single assign layout op. And then you have assign layout that is, or like if there's a convert layout of a function argument, right? That's like the main entry function. You can fold that convert layout operation into the client plain text tacking step. And then so that I don't think that part's actually done yet, but that's, a big optimization would basically say, have the client pack their data differently, and then we can have the compiler figure out how to do that. Okay, so this hoisting produces this like natural cost model that is currently very bare bones, but has sort of all the pieces in place. So if you have like an op with 2 operands and 1 result, and you're doing a layout conversion of the result after you're done with it, then you have maybe 2 new layout conversions that you need to do on the operands to make them both compatible with the desired output layout that's not being converted. And then the result of your op might be used by a bunch of different other ops, and some of them might require changes because they also now have a new layout. So there's the basically costs of layout conversions that happen at the beginning and end of the op. And then there's the cost of the actual kernel with the new layouts, which may be different based on which kernel you're using. And this is where like the kernel selection should happen, but isn't currently happening. And then so once you like add up all these costs, then the decision to hoist only happens if the total cost is negative. And so okay, there's the limitations here are the cost of a layout conversion is currently just like binary. So it's a 0 if you're doing the identity layout conversion, or if the system can recognize that you're going to fold it into a previous like convert layout op, or else it's 1. So the basically it would be minimizing total number of layout conversion operations. But since we have this later pass that implements the shift network for like actually would lower the layout conversion to a particular set of rotations, like a network of rotations, we could basically simulate what that would be in order to get its cost into this pass, but we haven't done that yet. And then there's currently no hoisting costs for, no hoisting costs. I'm not sure what I meant by that. There's no costs for op kernels that are like non-trivial. So I think we don't have a cost in there for like Halevi matvec. And this is part of some of my reservations, is that like we now have 2 different passes in the pipeline where like there's kind of still an open question about what kernel are we going to use, and it's not clear where that decision needs to be made. Okay, so finally we have the convert to ciphertext semantics. So this is the step where we implement the kernels, where we lower all the lineage ops and we lower all the layouts and all of that stuff to like, so once this is done, then everything is happening in the ciphertext domain. So the one thing that I noticed early on was that the type conversion that we apply that realizes the layout, it could change the types from tensors to different tensors. So we need a type conversion, so it needs to be a dialect conversion pass. But you actually can't implement the linear algebra op kernels without also having the type conversion from data semantics to ciphertext semantics. So those 2 operations have to happen at the same time, or the IR just won't verify and nothing will make any sense. And so that's what this pass does. It's implements the kernels we have are currently matrix vector multiplication via Halevi, lineage reduce via the rotate and reduce. So it will like rotate along the right dimension, and then do like the logs. So this is in our, we already have a pass called rotate and reduce, but this takes one of those kernels and implements it there. The tensor extract and tensor insert operations, which were, I think, a big pain for Hongren in that they were previous, like we had used to have BGV extract, or we still do. And so that will be gone because now tensor extract is in this pass and it will implement as like mask and rotate, which we don't want these ops in our kernels anyway, but we have them because we do some like extract a scalar from a tensor as like in the middle of an FHE program, and that's the only way to do that. And then we have lowerings for assign layout, which will do the plain text packing, and then also convert layout, which lowers it. Actually, it doesn't do the whole implementation of a layout conversion. It lowers it to an op I call tensorx.permute. And then there's a later pass that implements the permute operation via shift networks. So that basically takes the layout conversion and says, okay, here's the actual like expanded permutation of the slots that you need to implement. And then that's the input to the shift network pass. Okay, so the limitations, the things I don't like about this pass. The first thing is that the assign layout implementation is quite a bit messy. So all of these like insert new dimensions, do padding, do replication, and then apply the layout map results in like a really big IR that I don't think is necessarily that healthy to have all like in the same place in like one big pass. And then also things happen like, I don't know, I've noticed some like rough edges with MLIR. So like if you want to do something like take a slice of a tensor and pad it or replicate it throughout some larger tensor, then we have a bunch of like tensor insert or tensor insert slice operations. Like and like if the input, like in our data, we have like vectors of size 8 going into tensors of size like 1024 or something, but that still adds like a huge number of operations just to like do this and materialize this. And I think part of the issues, right, like MLIR, if you have like a tensor concat op that is freaking huge, then like with like a whole bunch of variadic operands, then like some things start to go slower. And then I can't implement these as loops yet because the noise system can't handle loops. And so that's like a whole other topic that we have to cover. But anyway, so I'm like not happy with exactly how this has all turned out, but at least it's working and I can actually run things and they do what I expect them to do. Yeah, okay, I mean, so I have via this pass, I had to design this whole context-aware dialect conversion thing. And then the way that I make it work in this pass is once an op is processed and has been converted from data semantics to ciphertext semantics, like I said, you can't tell from the type alone. So the type converter gets very confused. And so what I did here was after each op is converted, I add a materialized attribute to the op to tell the system, don't touch this op again. And then at the end, I clear all those away. It's not particularly elegant, but it works. Yeah, so okay, most of the kernels that I've implemented don't yet support multi-ciphertext variants. So I think I mentioned this earlier, but it's I'm not actually sure like how to support these in a lot of ways. So I think we'll have to either split them up into separate like data types or come up with more complicated kernels. And then there's a bunch of choices in here that are made about like rotation key management. So like, for example, the Halevi-Shoup kernel, you can lower it in a bunch of different ways. You could lower it as a loop where it rotates the ciphertext by 1 each time. You could lower it as an unrolled thing where it says, okay, I'm going to rotate by 1, rotate by 2, rotate by 3. Those have different impacts on like hoisting, the implementation, you know, of like batch rotation hoisting. If you do it by with a loop, you get a smaller IR and you only need 1 rotation key. If you do it with all spread out, you have lots of rotation keys, but then you could do hoisting. And I'm just like sort of making a decision without knowing exactly. I think I did the flattened one where it shows all the rotation keys, and I thought maybe a later pass would optimize for that, but and that also seems kind of hard. So okay, there's some issues there, and yeah, so we have some kind of nitty-gritty issues about how we represent the kernel that have impact on the rest of the pipeline. Okay, so I think this is my last slide. I'll highlight 2 of the concerns that I have about this, and then just stop and open the floor to discussion. So I mentioned the layout representation, I think, is not ideal, and I don't know what exactly I could do to make it better. But right now, it's the layout maps from data indices to plain text indices, and some layouts are easier to represent the other way. So if you start from the ciphertext indices and then you map to the data indices, then the Halevi-Shoup looks a lot simpler and more familiar. You don't need as much complication around replication, because if your ciphertexts are big enough, then if you're doing replication, then your ciphertext index set as a domain for your function will allow you to, by being a non-injective, it will just like naturally represent replication. But then there are some cases in which starting from the data and going to the plain text is easier. So I feel like maybe there's a way to have both. I don't know. And like maybe there's a way to like systematically invert one of these mappings when you can, and that could be useful. But yeah, so it's unclear to me exactly what to do with this, but I was going to explore that once I get this thing finally working and in. And then the second concern, I think the biggest second concern, is that the joint decision of the layout and the kernel selection still has no answer. And I think the direction we're moving for now is to just pick the best kernel for each op by default and force the layouts to comply by doing layout conversions. That is in line with the rest of the research literature, I feel, because the people who actually do layout plus kernel selection do brute force optimization effectively on their subset of their layout representation space. And so in the meantime, we can sort of make the system more flexible so the user can specify a kernel at the front end if they want to. But I think, yeah, like figuring out, like, I don't have an answer to how the pipeline would look different if we need to optimize for this. Like obviously we need to do it at the beginning before all of these passes I mentioned, because they are all fix the kernel, but I don't know what that would look like and how you would be able to tell what's the right thing to do. Okay, that's my slides. Let me go back to sharing the notes. Hold on. There we go. Okay, I will stop talking and open the floor for discussion.
I mean, first of all, thank you for suffering through that despite your obvious conditions. So yeah, thank you so much. I have another fun like layout thing to throw into the mix, which is that now with the new mapmol approaches, right, we're no longer just doing SIMD full CRT, full CRT matching. We're also using coefficient packing, like non-packing.
This is with Craig / I forget the other guy's name.
Like,
yeah, the new mapmol kernel.
Yeah, so I think I have a feeling it's going to be fairly easy. It's probably just going to be a toggle because you can't really do much with coefficient packed ciphertext other than to add them, or maybe do some shuffling with them. But yeah, I think
convolution. Yeah,
but I think in general we do need a way to represent them, even if it's like maybe it's like in the like alignment thing, it's just a flag. I don't know.
So
this was the bicyclic encoding one, right?
No, that was not. That's a different one. Bicyclic encoding is still slot. This is the it's the one where they just like represent ciphertext matrix multiplication in terms of just like regular matrix multiplication. The like from the inside view, right, or whatever, as like.
There's a Eurocrypt paper from last week that does that's the most recent one of these. Let me find out. Yeah,
we have an issue on it. But yeah, I don't know. Maybe Xian Young, since you have so much compiler experience, you can share some thoughts on how you think this problem should be solved.
Uh, I still don't know much about HIR, but we have also same problems with you, like layout operation, the construction of layout operations. Um, um, mm,
You could pass. It's fine.
yes. That's it. Thank you for your presentation.
I was also going to say, with the idea about the like joint selection of like layout and kernels, I think Jeremy, you had linked to me this like Flex FHE paper a couple of weeks ago, that maybe tries to use like an ILP to solve for the right layout. You had just done a search on it, but I did end up reading that, and I still think the conclusion is like no one is doing this in that way. So this is that Flex HE, something like that paper. And the thing is, though, that they are utilizing a framework of hybrid computation of like FHE plus MPC. So they don't care about rearranging after you're done with the kernel. So they have a much bigger search space, and they which like lets them do this ILP. But otherwise, like we have to do the whole like slot rearrangement, like layout conversion post kernel. Whereas they don't care about that because they're just going to extract slots from CKKS to MPC and do an MPC for the nonlinear part. So I kind of read that and I was like, okay, well, the problem still is this joint selection thing. Like I still don't think that it's can be done beyond like some heuristics maybe, or like the heuristics that people use are this is the best one. I just use that.
And I guess the funny thing is that seems to outperform all of the people who, spend 30 minutes doing a brute force search over their layouts in kernel space to figure out what the best, like, I don't know. It's very funny to look at those are all the older papers, and all the newer papers are like, we're not going to do that. We're just gonna pick the best kernel, and it turns out it's faster.
Yeah. I also feel like I've recently looked a lot into the sort of like large language model inference on the HE papers, and they use a whole variety of different like matmul packing approaches, right? And it doesn't matter because they all spent like well over 50% of the time bootstrapping, right? So it does matter to some extent, right? Like, but I think, yeah, I'm wondering if I don't think the compiler needs to be extremely good at this. It needs to not be extremely bad, right? I think as long as we can get some heuristics that work well enough to get a reasonable performance, I don't think anybody's going to like stop using HEIR because of that. The other thing is what we might think about, and this is sort of similar to what you mentioned at the beginning, like the last office hour, where it's like, hey, if I'm an expert and I know what I'm doing, but I don't want to like hand code everything, how can I tell the compiler what to do? And I think this is maybe something we need to think about is how do you tell I want this kernel here, and then have the system make it work for the rest of the code, right?
So I think the nice thing is that the layout propagation pass is basically already ready to do that. I don't know to what like I have to look at it in detail, but like it's set up very much to be like, okay, once a layout has been decided, then it can propagate outwards from that. And so like it would propagate forward to the like hard-coded layout, and then the hard-coded layout could keep like it's really just I'm going to propagate as much as I can forward and like stop when I can't propagate forward anymore. And so that is like very compatible with someone just like inserting a constraint in the middle that says, hey, you already have this layout ahead of time. And then the second layout optimization pass would do the reverse propagation of that to like try and resolve those discrepancies with like the default choice and the middle choice. Which I think that's actually a nice part of the design.
Yeah.
The other thing that I had discussed this with someone from Niobium, the idea of having like a kernel language for packing that's embedded in like our front end. So like, and that's like a much more ambitious project, but like that would then give the user complete control over the packing part of it for particular ops or for particular subsets of the IR, while not having to manage the bootstrapping placement, all of the other stuff around that we're going to be supporting. So I think that's like in scope, but I'm not a programming language designer, so I don't know how hard that would be.
Other sort of tangential thing about the layout system you'd mentioned about like the loop unrolling thing. So last week I took the time to read Sung Yun's papers, the capo and halo, in like actual detail. And so I found a lot of the ideas, like one, it's nice that the code's in MLAR, so it's very easy to navigate, but also some of the ideas, they can be implemented like a little bit piecemeal too. Like, so they can be implemented like on top of some of our existing passes. So there was things like in order to like reconcile loops, the problems that we were having with the MLAR type system, like that was the whole basis of the Halo paper. And the solution suggestions that were in that paper were pretty straightforward. And we talked about them a little bit in the review about like peeling the first loop iteration. So it's nice to know that that was part of the paper. And then also to reconcile the levels, there was like a systematic way of doing this to reconcile the levels of that within the loop iteration. It's not clear to me exactly how noise analysis and the other passes will decide to handle the for loops, but at least the ideas in the Halo paper will reconcile those types. So I don't really have like a full-on agenda beyond like welcome Sun Young to the meeting, and like part of me was just curious about why you were here, but also like that was just part of the like preserving loops in the kernels. I think shouldn't be a problem if we can implement some of those like Halo style type reconciliations and have loops look more like a black box to the noise analysis thing that change, levels, noise and levels in a systematic way.
Yeah, for context, the difficulty we're having with loops in the pipeline is that we have this ciphertext management system that handles like mod reduce and bootstrap insertion and like all the other like ciphertext management operations. And then it also does like noise analysis and parameter selection. And the noise analysis of a loop obviously is difficult if you don't have a loop of a very particular structure to maintain noise invariance and all of the other aspects of the ciphertext like across the loop. And so I think we want to have some means to keep that like well structured. And like I think like the example of like peeling off the first iteration of the loop, or like partially unrolling a loop and inserting like a bootstrap at the end of every like 3 loops or whatever, so that the noise is reset at the end of every loop, and that the noise analysis. So then if we have something like that, the noise analysis passes could operate still on IRs with loops in them and like provide some useful information there. You're still muted, Asra.
I was saying, yeah, Sunyoung has like context about how to do that bootstrapping placement, then plus all the optimizations to either like, for very short loops, just unroll them all if we're not utilizing all the levels, or to like only bootstrap up to the level needed for the loop. So I think all those ideas are like, it's just, again, nice that it's an MLAR, because you don't have to look at it like, some compilers like internal structure, like the pass exists in itself, just albeit in their dialect. Which is compatible with ours, actually. I think like it's not too different than our CKKS dialect anyway.
We probably wouldn't want to run this at that low level, right? We want to do it at like secret arithmetic.
Yeah, but it needs to have a dialect that has the like management operations in it. So basically,
right.
Yeah. As long as we have things like modulus switch and bootstrap and stuff like that. Jeremy, okay, so given like the layout system, and then there's also this bootstrapping placement, there's like lots of stuff going on. Where do we go next for like reconciling some of the bad parts of the layout system, or like, yeah, what's...
Yeah, I mean, my feeling is the like majority of what we want out of the packing system for now is to support all of the lineage kernels that show up in machine learning models. And I don't see anything about the layout system right now that would prevent us from doing that. So like nothing strictly needs to change. It's mostly my own personal, like I'm a software engineer and I want things to be clean. I don't like designs that have lots of fix me's and to-dos in them. Like where I want to go and take a second look and try to come up with something more elegant. And I think it might be worthwhile to wait until we have all of the kernels implemented before I do that, because then I will have a more complete picture of what we need to support. And so like really I've been driving this, all of the stuff I've been driving is just from wanting to support Halevi Shoop and like rotate and reduce style, like row, summing columns and summing rows of matrices. And then like I know there's going to be convolution, which, you know, people tend to represent this as matrix multiplication anyway, but then there's going to be bicyclic, all these other kernels that I don't immediately off the top of my head see any like problems there, but I think it's just worthwhile to wait until I get some more experience with that before trying to do like a complete redesign. But I think the biggest thing that I think that a lot of the system would be simplified if we switched the order of the layout map, starting from slot indices and going to data indices. I think that would reduce the reliance on this like replication stuff, which I think is the messiest part. Yeah, and then like I don't know, I'm like so in the weeds right now. I don't feel like I have the bandwidth to like start thinking about like original research for like the lineage, like the kernel selection and stuff. But I feel like most of what I've been thinking about that is improving and expanding the like ILPs that we have at like the management level, which is unrelated to packing, but that's I think of the world in terms of linear programming, which is like what else would you do? I mean, it would be some synthesis approach, right? Like the options that we have for like, there's a heuristic, right? Find some heuristic that works. There's a synthesis approach, which has been tried and is slow, but like maybe we can, I've always had the idea of maybe like implementing a core synthesis routine of our own that is, you know, more performant and is like aware of all of the idiosyncrasies of what we're doing to speed things up. I know that people have had a lot of just from like my own personal research, like modern, this is going to be random, but modern dependency resolution systems in like for like programming languages, and like they used to all be SAT solvers or like bad heuristics, and the SAT solvers were too slow and the bad heuristics were bad. And so then what people did was they re-implemented SAT solvers with domain knowledge about dependency resolution. And that was in order to make them faster. And now like they all do this, and they're all like custom SAT algorithms that know what dependency resolution is. And it's like, okay, like could we have like custom synthesis algorithms that know about FHE and can be faster for it? Like that's like probably like my best research idea. A very hazy fuzzy research idea is like custom design these for FHE. Whereas the alternatives are like using like black box solver methods and formulating the problem appropriately, or coming up with a better heuristic.
Another somewhat like low hanging, not as like pipe dream in the sky, like big picture thing is I think a lot of the what we benefit from being a universal compiler is that we have a lot of information in our IR. Like we have this layout attribute in our IR. Where I think when I was reading Halo, there's like some optimization to do bootstrapping better in loops, where you can pack multiple ciphertexts that need to be bootstrapped at the end of the loop into one and just bootstrap that one together. And then after that, you have to unpack everything and then cyclically rotate everything, right? So then you're doing a lot of masks and consuming a bit of multiplicative depth. But if we have some knowledge about our layout attribute throughout our kernels and realize perhaps we don't need to do cyclic repetition, or we don't need to do some of this masking, then we might have like wins there of maybe we can reduce some unneeded operations if we don't need
like
to
leave it in the packed form, and like if you're just like adding things, then you can leave it in the packed form and like do some
Right.
Yeah.
Like unneeded math, unneeded repetitions going on where like other compilers, because they don't propagate that information and aren't doing analysis on it, just require that to be done.
Yeah, and I guess the other idea I've, since anybody talks about at Google right now is AI, is like, okay, could we have some sort of like AI in the loop system that that would happen offline, figures out a good packing for like a really important program that you have that you only need to compile once, and then like, I don't know, they do all these things where it's like, okay, the LLM is like suggesting a simplified version of like a more complicated, like, I think there could be something in there, but yeah, that's also kind of pie in the sky, and seems really difficult to have in the compiler in the loop. So maybe some sort of, like, I think the other idea that I guess ties into that more generally is just having runtime profiling be incorporated back into the IR. And we're sort of talking about doing this for like CKKS, right? Like if you want to do CKKS parameter selection, you need to kind of have runtime profiling. But just more generally, you could have like runtime profiling where you're experimenting with the layout, you're running the program lots of different times and then seeing how that changes, and then having either like a classical black box super optimizer like Vizier is one of these systems, to suggest changes to the layout, or else using something more complicated like a LLM in the loop. So this, I think these would all be like very cool, sort of out of scope, I think, for this year, but at least for me, I've got too much other stuff to do, but like the idea of having stuff outside the compiler be ingested into the compiler, I think is kind of cool.
I mean, I think we also need that a little bit with like the range analysis, right? Like we'll need
Right,
to
that's
do-
what I was saying, is the exactly, yeah, for CKS parameter selection we need something like that, and then having, but like we could, I don't see why we couldn't do something like that for packing as well.
Yeah. There's like, I think there might actually, that F Flex HE paper might have done something like that actually. But I can't remember offhand.
Okay, we are over time. I'm gonna stop the recording.